If you would recall, yesterday we started talking about Lagrange multipliers and constrained optimization. This is where we're trying to optimize, that is, maximize or minimize some objective function, but subject to some constraints. To do this, rather than, we might not have an optimal point at a critical point, although this process will find critical points. What we want, the short story is, the TLDR, is that we want the gradients of our function, our objective function, and our constraint function to be going in the same direction. That is, I want the gradient vector of the objective and to be a constant multiple, a scalar multiple of the gradients of our constraint function. Now, this is going to have a number of variables equal to however many variables we have, 2 in this case, plus a third one, this lambda, the Lagrange multiplier. So our third equation comes from our constraint. So we want the gradients to be going in the same direction. That creates 2 equations and 3 unknowns. And our constraint equals C is our third equation. So we have 3 equations, 3 unknowns, presumably we can solve. Here's how we want to think of Lagrange multipliers. I want the gradients to point in the same direction. We want the gradients to point in the same direction. Think about what the gradient is telling us. Think about what the gradient is telling us. And remember, we want the gradients to point in the same direction. That's what this statement says. We do a few problems, and then it starts to make more sense why we want the gradients to point in the same direction. So in addition to this, lambda is the Lagrange multiplier. If we think in terms of magnitude, so lambda is a scalar. We can see it's a scalar by the way I'm using it. Gradient of f is a vector, gradient of g is a vector. Lambda must be a scalar because I just have lambda shoved up against a vector. And the only way that makes sense is if lambda is a scalar. So let's think in terms of magnitudes, what lambda represents. So if the gradient of f is equal to the lambda times the gradient of g, then the magnitude of the gradient of f is equal to lambda times the magnitude of the gradient of g. So if we just kind of solve for lambda by dividing by the gradient of g, lambda starts to look like a rate of change, which is how we can interpret it. Lambda is the gradient of f divided by, or the magnitude of the gradient of f divided by the magnitude of the gradient of g. We had to drop magnitudes on all these because it doesn't really make sense to divide by a vector. But if we look at lambda, we see the gradient of f divided by the gradient of g. And that makes it look kind of like a rate of change, how much the function is changing with respect to how the objective is changing. So we wanted to try, let's take our old problem, the problem that we had before, and see if it fits with this new, see if we get with this new process. We wanted to minimize the surface area. So remember, the point is not to solve the problem. This is a problem that we already solved. Whenever you learn a new process that might be able to be used on an old problem, You should use the new process on the old problem to see if it still works, or figure out what's different about the new problem. Always use your new problem on a new process on an old problem. So our objective function in our Lagrange multipliers, our f, it's going to be of r and h. Is going to be 2 pi r squared plus 2 pi rh. And our objective function, or sorry, our constraint function so I need to build the gradient of f, and I need to build the gradient of g. The gradient of f, I need f. I need our two first partial derivatives. So with respect to r, I get 4 pi r to the first plus 2 pi h, and f with respect to h is just going to be 2 pi r. So our gradient of f is 4 pi r plus 2 pi h I plus 2 pi r j. There's our gradient of f. I need the gradient of g as well. So I need g with respect to r. That's going to be the derivative of r squared is 2r, so 2 pi rh, and g with respect to h is going to be pi r squared. So our gradient of g is going to be 2 pi rh I plus pi r squared j. So now we can build, now we have all the parts, we can build our system of equations. I can take the gradient of f equals lambda times the gradient of g. So I'll take the gradient of f equals lambda times the gradient of g. And I also want my constraints where g is equal to the constant. So here's a system of 3 equations in 3 unknowns. I say 3 equations because that first one is a vector equation, and we're going to turn it into 2 equations by saying the I components must be equal and the j components must be equal. So it's just a summary of 2 equations. So this first one means that 4 pi r plus 2 pi h is equal to 2 pi rh. Lambda times 2 pi rh. So I'm going to take this 4 pi r is equal to lambda times 2 pi rh. There's the I component on the left, and then the I component on the right is lambda times 2 pi RH. An equation in R and H. Then we're going to take 2 pi R and the pi R squared. Then our third equation is just our constraint. So there's our system of 3 equations with 3 variables. Any questions so far? This is all in service of making the gradients point in the same direction. Direction of maximum change on one of them at the same point as the direction of maximum change on the other one. Wonder twin powers activate. That's going to be where our maximum or minimum is. Introducing this new variable of lambda is us saying I want the vectors to go in the same direction, but they don't have to be the same size. So lambda is how we control the size. It scales one of them up or down so that we just care about direction. That introduces a third variable, but fortunately we have a third equation from the constraint. So that's where the 500 comes in. Any questions? Our standard operating procedure for solving this system is to eliminate lambda. Lambda is always going to be sitting there by itself. All the other variables might have exponents and other weird shit going on. So we're going to eliminate lambda. I'm going to solve for lambda in each of the equations and then equate those equations. And then hopefully we'll see something familiar. So the standard operating procedure . We solve for lambda in the first 2 equations and then eliminate lambda by saying lambda equals lambda. That's going to be our standard operating procedure. One of the things I really like about Lagrange multipliers, which is why I spend a lot of time talking about Lagrange multipliers, is that we take a problem, and this is one of the things that we care about in multivariable calculus. Multivariable calculus is taking single variable calculus and doing it on more variables. The reason for this is that more variables might mechanically complicate things, but more variables makes it easier to work. It gives you more room to work. We're introducing a variable here to help us solve a problem. Sometimes it's useful to have more variables. There's also a great integration technique that I've really been hoping to include. Especially now that y'all have partial derivatives. So our standard operating procedure is going to be to solve for lambda in the first 2 equations, and then just make an equation that lambda equals lambda. That eliminates lambda. That takes 2 equations and 3 variables down to 1 equation and 2 variables. And then we'll have 2 equations and 2 variables. So let's see that happen. So the first equation is going to tell us that lambda is 4 pi r plus 2 pi h divided by 2 pi r h. And the second equation gives us that lambda is 2 pi r divided by pi r squared. So just take the 4 pi r plus 2 pi h, oops, there it is, and divide by the 2 pi r h. And then just take the 2 pi r and divide by pi r squared. What's that? Yeah, we're going to simplify. So let's see, what can we get rid of? We can get rid of a 2 pi all the way through here. Let's see. Let's see which one we like better. So I'm going to, if we split this up. So here we're going to get 2 over h. And here we're going to get 1 over r. And on this side, lambda is equal to, see the pi's cancel out, one of the r's cancel out, 2 over r. So this is like our lambda from the first equation. This is our lambda from the second equation. I don't want to put subscripts on because they are in fact the same lambda. So we eliminate the lambda by saying these two lambdas are the same lambda. So we make the lambda equals lambda. Any questions? This is in the category of solving nonlinear systems of equations. And our only instruction for solving nonlinear systems of equations is just try to eliminate variables. Do something. The most important thing that you can ever do on any math problem ever. Just do something. Now, when we look at our previous problem, when we had, scroll down, doesn't look right. This looks different. But remember, in our previous method, we took our constraint and plugged our constraint into our objective to eliminate a variable that way. So it's not surprising that it looks different. So here's an equation. 2 over h plus 1 over r is equal to 2 over r. If I multiply everything by RH, that'll give me 2r plus h is equal to 2h. At this point, we should be worried about r and h being 0, but we know that that's not going to be the case, because if r and h are going to, either one of those is 0, then our volume is 0, and that is not possible. So we are okay multiplying by RH. We know that we're not multiplying by 0. So let's see. What this means is that h is just equal to 2 times r. Thinking back to the work that we did yesterday, this is the result that we had. We had a, I know y'all are trying to copy it, and I keep flipping pages on you. So here, go ahead and copy that down. Psych. Go ahead and, no, this time for real. No, psych. So now I'm just being a dick. So remember what we got was that our radius was 4.3 and our height was 8.6 plus some other stuff, which was about twice as much as the other. And we got this kind of cylinder that was trying to be a sphere, because spheres are nice and efficient for using surface area, not for building in general. So this matches what we had before. We could use this. Remember, the other equation that we have is our constraint, which said that pi r squared h is equal to 500. So if h is equal to 2r, I can plug that in and solve for, I can use that to eliminate one of the variables. We'll just take the 2r and plug it into our constraint. Now I've eliminated r from the third equation. Sorry, I've eliminated h from the third equation, and then we can solve. So we got the same thing that we got yesterday, which is good news. It was supposed to come out the same way. If you do a problem two different ways and you get two different answers, one of those ways is wrong. And of course, that doesn't eliminate the possibility that both are wrong. Question? I do want to make a note that it is okay to multiply by RH because neither one of those is going to be zero, because we are looking ahead and we know that our volume is supposed to be 500, and that won't happen with a radius or a height of 0. So we are okay to do that. Most of the proofs that say that 1 is equal to 0 rely on multiplying or dividing by 0 at some point, usually multiplying by 0. Now, some of them divide by 0. Either way, bad stuff. They're really variations on that same thing. So remember, even though we had already solved this problem previously, that wasn't the point. We've introduced this new process, Lagrange multipliers. We've introduced this new idea, make the gradients point in the same direction. And we should make sure that it works on a previous problem. The reason that we didn't need this to solve the previous problem is that our constraint was so convenient. Our constraint was being very agreeable. We could take our constraint and solve for one of the variables. That's why it worked. So the reason that we didn't need this in the problem the reason we didn't need Lagrange multipliers 2 semesters ago when we did this problem is that we had this. We had the volume pi r squared h is equal to 500. And it was easy to solve this for h. We were able to solve the constraint for one of the variables and eliminate it from our objective. We were able to rewrite the objective into one variable. That's why we didn't need this originally. That's why this particular problem was chosen for this process, for this optimization, the constraint optimization process. We were able to write our objective in terms of one variable. We don't always get to do that. So we want to note that we're not always going to be able to do that. When we can, we probably should, because it drops things down to a single variable, and we're very efficient at solving problems with a single variable. Not necessarily because it's better, it's just that we spend more time doing it. Any questions? Comments? Yes. Technically, but it wouldn't have, so mechanically, yes, absolutely. Because there's nothing stopping us from just like throwing in partial derivatives out of context, right? At this point, you know what a gradient is and know what it's supposed to mean. And to do that, you had to know what the partial derivatives represent. But mechanically, we could have done this process. It wouldn't have meant much, but one of the things that we definitely know is that we can absolutely teach people process out of context. Because there's like the process and then there's the context. And we tend to not worry about, sometimes we tend to not worry about why things are. This is why, for the most part, we struggle with algebra. There's no reason that we should be struggling with algebra if we're proficient in arithmetic. Because we should, if we understood what was going on in arithmetic, if we understood what numbers represent, then algebra should just be, hey, remember arithmetic? Yeah, it's base X now, right? But for the most part, you can't be like with children when we're teaching them arithmetic and then eventually algebra. Even though they know how to count and even though they're proficient in arithmetic, they don't really understand what's going on. They've just been taught a lot of process. Does that make sense? So kind of yeah, but kind of nah. If we want to make, if our goal was to get you to solve problems, then absolutely. We could have just like removed the context. Don't worry about what gradient is. I wouldn't even said gradient. I would have just said, do this weird derivative trick. I wouldn't have even said partial derivatives. So I'd just be like, oh, okay, let's pretend that h is a constant. And I wouldn't frame it in terms of partial derivatives. I just pretend h is a constant, take the derivative with r. Now take the derivative with h. And people would be like, oh, why though? He's like, well, don't worry about that. We're learning process, right? So yes, and that would have expanded the number of problems that we could have done. We could have done more interesting problems. But then we would have got to multivariable calculus and it's like, oh, hey, remember that process? And then I would have had to fill in all those blanks. And it's debatable whether that process, knowing the process, would be helpful later on. Because a lot of math does present like a Marvel mid-credit scene. It's like, oh, here's what's coming up next, right? We do all this algebra and set it up in certain ways. And we might explain certain things in a way that sets us up for the next class, right? Like a mid-credit sequence in a Marvel movie. That we're setting up the next class. But I think that then the thinking, because we don't all progress through calculus, like a complete pre-advanced math curriculum, we tend to stop people once they get through algebra. It kind of, that's why we start to miss the point on a lot of the stuff that we do in algebra. This is not to say that algebra is just going to be, is just a vehicle for the next thing. It stands on its own as a process of human thought. But if we can stop thinking in terms of these classes and these classes only, and start thinking in terms of an elementary education in math, going from counting and naming numbers through calculus, if we could think of that as our elementary course in math, I think we would be better. We would be better off. I think too often we say, well, we just need people to stop at algebra, and that kind of misses the point of algebra. And most importantly, we stop at algebra, missing the point of our elementary education in math at a point when people are going to start questioning the things that they're asking them to do. Now, I think that's a big part of it, because when do we start teaching you algebra? For the most part, when you're teenagers. And when do you start questioning the dumb shit that adults ask you to do? When you're teenagers. Some of you are more advanced and started questioning that earlier, but in general, that's when people start questioning things. They start looking at the teacher and saying, no, fuck you. I don't want to know that. Do you know what I mean? So yeah, totally. There's nothing funky going on here, right? There's nothing that we couldn't do. It's like taking derivatives. Y'all are good at taking derivatives. I got a Calc 1 class. They could take derivatives. I'm like, oh, no, H is a constant. And I'd be like, oh, okay, like a K? I'm like, oh, yeah, it's just a K that had like these two like smashed together. H is just a heated up K, because that one that goes up kind of melts and kind of like falls down and it kind of bends a little bit, right? So process-wise, there's nothing interesting going on, right? I could tell because everybody's like falling asleep as soon as they start getting into the process. Like, okay, we'll solve for lambda in each of these equations. And everybody's like, oh my God, you can't do this to us this early in the morning. We're going to fall into such a deep sleep, we will be in a coma. So that's why I had to choose a shorter problem, right? So that we get right before the coma. Michael, there's what we found yesterday. And they're like, well, wow, yeah, yes, I remember, yes. What are you talking about? Show me. So yeah, great question. It's like we could totally do this earlier, but we have this, we want to kind of put it in context. We want to be able to put it in context. I want Lagrange multipliers not to be this weird arcane process, because it's kind of weird and arcane process-wise. I want the big idea. I just want the gradients to point in the same direction. That's what I want you thinking about during this process. It's like, oh, why is Leach asking us have they're not the same size? Let's do this. Why do we want the gradients to be pointing in the same direction? Because that helps us think about what the gradient represents on a surface. Good question. And this is the curse of being in my class. I can't answer a question like yes or no. How's everybody okay? Constrained optimization. We want to maximize or minimize the thing, but subject to some constraints. All right, this is what I want you thinking about. Here's our Lagrange multipliers. The gradient of f is equal to lambda times the gradient of g. If you're wondering, it could have absolutely gone the other way. We could have made this, and there's probably some universe where they think of rate of change differently. They're like all slope is run over rise, right? And it's really weird. And they're like all the gradient of the constraint should be lambda times the gradient of the objective. I don't know. I don't think I want to live in that world, but question? No. That's just us. That's just a tool for us to think about what lambda might represent. Just, yeah, we just want to think about what this weird parameter represents. We've introduced a parameter. What could it possibly mean? Why would we do this? The reason it sticks out, one of the reasons Lagrange multipliers stick out is that this tends to be the first time we start introducing parameters that we kind of immediately get rid of. That's like the thing. Like when we talk about parameterized equations, when you just describe a curve with describe a circle as x equals cosine t, y equals sine t for t between 0 and 2 pi, right? We're introducing a parameter, but that parameter doesn't just go away. This parameter is like, well, hey, introduce this parameter. It's like, ooh, that sounds like it's going to be important. First thing, get rid of that parameter. And it's like, that's kind of weird to do that. We're introducing a parameter functionally just to do a thing because we know it will do the thing that we want it to do. This is just like when you were learning Feynman's integration style, where you differentiate under the integral sign. I know you didn't do that in Calc 2. Did anybody do that? Integrate by differentiating under the integral sign. You kind of need partial derivatives to do it, but you don't really need partial derivatives to do partial derivatives. I trick my Calc 1 class into doing partial derivatives because I'll be like, oh, hey, here, what's the derivative with respect to r? It's like, well, what do we do with h? It's a constant. Okay. And everybody was fine with it. Everybody was like totally fine with it. That's called the Paul-Muller technique, but that refers to a commercial that none of you are old enough to have seen. So I don't know why I keep saying that. All right, that's going to do it for today. Gradients going in the same direction, objective and constraints. That's the Lagrange multiplier game. Everybody have a good day, and thanks for playing.